Welcome to Full Spectrum Science Shorts. I'm your host, Ron Hipschman. Today, tides. The moon and sun do have an influence on the Earth. This has to do with the influence of gravity. While we don't personally feel this influence, despite what astrologers may say, larger objects like the Earth do respond to these attractive forces. I'd like to note that the diagrams in my presentation representing the sizes and distances of the sun, moon, and Earth are wildly out of scale. For a better picture of this, see the Full Spectrum Science Shorts video titled, "That's Why They Call It Space." The gravitational pull of the sun and moon get weaker with distance, just like the color gets weaker here. It follows something called the inverse square law. What do I mean by this? Well, if you were standing on the surface of the moon, gravity pulls you toward the moon's center with a certain force. If you put a scale under your feet, we'd call this force your weight. Let's say that you weigh 100 kilograms. Now, say you build a very tall tower, 1 moon radius in height, so you're now 2 radii from the center. If you climbed that tower and tried your scale again, you'd notice that your weight had dropped to not 1/2 like you might expect, but to 1/4 what it was on the surface, or 25 kilograms. Double the distance to the center of the moon, 2 squared is 4, 1/4 the pull on you, and hence 1/4 the weight. Inverse square. If you added more to your tower, so you tripled your distance from the center of the moon, you'd weigh 1/9 what you did on the surface, or only 11 kilograms. 3 times the distance, 3 squared is 9, 1/9 the weight. The force of gravity falls off by the inverse square of the distance. The moon's influence never reaches zero, no matter how far you travel. It just becomes so weak that it's overwhelmed by gravitational forces from other bodies. The poet Francis Thompson stated it this way: "All things by immortal power, near or far, to each other hiddenly linked are, that thou canst not stir a flower without troubling of a star." The weakening gravity of the moon pulls more strongly on the waters nearer the moon than on the Earth, here in yellow, and more strongly on the Earth than on the waters on the far side of the Earth. Well, how does this affect the water? The tides are caused by the difference in pull between the near side of the Earth and the far side of the Earth. That's a bit hard to see here. To look at the forces on the water, we need to subtract out the average force from all 3 forces you see here. The force in the middle, the force on the Earth in yellow, is the average force. Subtracting this force from the bigger force on the nearer side of the moon gives us a smaller force, but still pointing at the moon. Subtracting the average force from itself leaves 0 force on the Earth, removing that force arrow completely. And subtracting the larger average force from the smaller force on the far side of the Earth leaves a small force, but pointing away from the moon. Look at these forces. This is the net force on the waters of the Earth. These forces will stretch the oceans, causing 2 high bulges and 2 low areas. Again, if we consider only the moon, its effect is to stretch the waters, creating 2 high tides, one pointing at the moon and one pointing away from the moon, and 2 low tides at right angles to these. The moon isn't the only actor on our stage, though. We also need to consider the sun. Although the gravity of the sun is much stronger, the sun is also much farther away. What's important, though, is that the difference in the sun's pull from one side of the Earth to the other is much smaller. This results in solar tides being less than half as high as lunar tides, like you see here. Of course, we must consider both lunar and solar tides together. As the moon revolves around the Earth, we see various lunar phases depending on the relative positions of the sun and moon. At new and full moon, the alignment is like you see here. The sun, moon, and earth are all along a straight line, and the sun and moon pull along that same line. So the moon's effect is to stretch the waters like you see here. And the sun, pulling in the same direction, enhances the pull of the moon, stretching the waters of the ocean even more. This creates higher high tides and lower low tides at new and full moon. These are called spring tides. This has nothing to do with the season spring, but rather because the water springs up towards the moon. At the first or third quarter moon, the pull of the sun and moon compete, pulling in different directions. The moon still creates the biggest tides, but the effect of the sun, though smaller, reduces the lunar tides, creating higher low tides and lower high tides. These are called Neap Tides. Now, it was a little hard to see in the previous diagrams, so let's look at the difference between spring tides and neap tides again. Here, close to new or full moon, the sun and moon are pulling in the same direction. The high tides and low tides are both higher and lower. There's a bigger difference from low to high tide. Close to first and third quarter moon, the sun and moon pull at 90 degrees to each other. The sun's influence is less than the moon's, but its pull partially cancels the moon's pull, lowering the high tides and raising the low tides, so there's a smaller difference between them. Generally speaking, the tidal bulge follows the moon. From new moon to the next new moon takes 29.5 days, so the Earth rotates 29.5 times within the tidal bulge as the moon orbits around the Earth. As passengers on the rotating Earth, we are carried through the high and low tides. We know it takes 24 hours to go from, say, noon to noon, so the time from low tide to high tide should be 1/4 this, or 6 hours. But the moon is also revolving around the Earth at the same time, so it takes an extra 50 minutes every day for the Earth's rotation to catch up with the moon. The extra time, 12 minutes, between tides is because of this motion of the moon. Here, we see a panorama of the bay water from the pier of the Exploratorium at low tide. Tides in our area can vary over 9 feet from low to high tide. Here's the view at high tide. Quite a dramatic difference. Maybe it would be easier to see with both photos on the screen at the same time. At low tide, the pilings are sticking perhaps 6 feet out of the water. At high tide, they're hidden well below the surface. If we charted the tidal variation for 3 days, this is what you might see during a typical spring tide. The maximum numbers on the left side of the chart are the highest and lowest possible calculated tides for our location, not counting storm surges. The highs and lows on the right side of the chart are the highest and lowest within this 3-day interval. A week later, we'll have neap tides with their reduced amplitudes. The highs are not as high and the lows are not as low. Let's overlay the previous curve in red so you can compare them. The widest tidal range in the world can be seen in the Bay of Fundy, Nova Scotia, Canada. The average is a little over 42 feet between low and high tide. The sun and moon don't pull any harder on Nova Scotia. It's a matter of geography. The Bay of Fundy forms a natural funnel. The incoming volume of water gets squeezed into the narrower and narrower mouth of the bay. At the same time, the depth decreases from over 600 feet to only 150 feet. Let's look at the tides at Halls Harbor, way up at the northeastern end of the bay. This video, which is sped up by a factor of 360 times, shows these amazing tides. Hall's Harbor is quite far north at 45 degrees latitude, so in the summer it experiences over 15 hours of daylight, plenty for us to see a complete cycle of low to high and back again to low tide. Here you can see how important it is to have a floating dock. And we've almost reached high tide. Here we are at high tide, about 12 hours and 30 minutes later, and the tide is now decreasing. One of the things I find amusing is at low tide, when all the water drains out of the harbor, it leaves a lot of the sea life resting on the mud flats of the harbor itself, and you'll see the seabirds rush in to pick off all the fish and sea life there. Watch, here they come. There they are. Like the Bay of Fundy, tides can be compressed and run up the mouths of rivers, creating a wave called a tidal bore. This is the mouth of the Qiantang River in China, near the city of Hangzhou. Known for centuries, this very large tidal bore, the largest on Earth, has even become a tourist attraction. As you can see in a little bit, they're well prepared for this phenomenon, with high banks and sloped wave absorbers. The bore you see here was the largest one in 10 years and drew thousands of people to the spectacle. Let's watch some of this incredible phenomenon. Here you see those sloped wave absorbers. Again, this is an extraordinarily high tidal bore. But still, it's an amazing demonstration of the power of the moon and sun's gravity on the waters of the earth. This tidal bore has become known for other things as well. It attracts surfers from all over the world. It's quite a ride on waves up to 30 feet tall, traveling 25 miles per hour for over 15 miles inland, taking these hardy surfers over an hour to complete their surf. That must be an amazing experience. The high and low bulges of the tide I've been showing you are obviously gross oversimplifications. The geography of the Earth, with its varying ocean depth and complicated coastlines in the way, make predicting tides much more complicated. This beautiful visualization of tides in the world's oceans by Svetlana Erofeva of Oregon State University shows the complicated sloshing around of tidal waters. This is one day of tides. Note that mid-ocean tides rarely rise or fall more than 3 feet. Please visit their website for up-to-date data and visualizations. I'd like to refer to Paul Doherty, one of our former teachers here in our Teacher Institute. One of his taglines was, "It's more complicated than that." And this is certainly true of tides. We've gone through the basics, but there's lots more to learn. There are even complete books about tides, but you better have your math hat strapped on for this book. In the next Full Spectrum Science Shorts edition, we're going to continue to explore the very high and very low tides called king tides, and the reasons for this amazing phenomenon. We hope to see you then. Thank you for viewing Full Spectrum Science Shorts presented by the Exploratorium in San Francisco. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.